Hello everybody and welcome to our video on rules of logarithms. So in particular, the rules we're going to primarily talk about in this section are the product, quotient, and power rules for logarithms. And these are the natural, let me try to say that again. These are the natural analogs of the rules for exponential functions. So when we look at our rules for exponential functions, a to the x times a to the y equals a to the x plus y, the logarithmic product rule is log base a of x times y equals log base a of x plus log base a of y. So what you should notice is that just like everything else about logarithms, these are inverse functions. They switch inputs and outputs. So their rules also switch the inputs and outputs of their operations. So notice that here, multiplication is outside of the two exponential functions, a to the x times a to the y, with addition inside the input of the function. For the logarithmic functions, the rule is just x times y, the multiplication is inside the function, and the sum is outside of the function. You're switching inputs and outputs. So they're essentially the same rules, just rewritten for the inverse functions. So the quotient rule, similarly, division for the exponential function is outside of the two functions, and it's related to subtraction inside the input of the function. But for the logarithmic functions, the division is inside with subtraction outside. The power rule, a to the x to the r power equals a to the x times r. You have an exponent outside and multiplication inside. And for the logarithmic functions, you have an exponent inside and multiplication outside. So essentially what I'm trying to say here is that if you have the product, quotient, and power rules for exponential functions memorized, then you should also have the logarithmic functions memorized because you're just switching the inputs and outputs of the rules around. So one thing I suggest practicing is like write down an exponential rule, and then without looking at anything, see if you can figure out by writing out the exponential rule, what does the log rule look like? So go, oh, well here multiplication was outside, so now it's inside, equals, and the addition was inside, and so now it's addition outside. And if you can do that process for each of these rules, then they're going to stick with you a lot easier. Now with that being said, the justification I've given here isn't really a proof, right? It's not rigorous, it's just the gist, the idea. So we're going to prove one of these rules rigorously, and that's going to be the product rule for logarithms, and the proof of the other two rules is very similar. So the product rule, we're going to start by giving names to log base a of x and log base a of y. So in our product rule, we're looking at log base a of x plus log base a of y. And so we're just going to rewrite log base a of x as just u and log base a of y as v. Then what does that tell us? Well, if we switch our inputs and outputs, then we get x equals a to the u when we switch to the exponential form, and y equals a to the v. So now, if I take the product x times y, that's going to be equal to a to the u times a to the v, which gives me x times y equals a to the u plus v. And so now if I take log base a of both sides of the equation, I get log base a of xy equals log base a of a to the u plus v, and log base a of a to the u plus v is u plus v. But u was log base a of x, and v was log base a of y, and so we finally get log base a of xy equals log base a of x plus log base a of y. So if you think about what we've done here, essentially what we did is we switched our logarithmic forms to exponential forms, then we applied the product rule for exponents, and then we switched back to writing these as logarithms, and this is the rule that we got, right? So just like I said, all these rules are just, you're switching the exponential rule into the logarithmic notation. Okay, so with that, let's go ahead and start applying some of these rules. So example 1, given that log of x equals 3 and log of y equals 4, evaluate log of x squared y cubed. So I need to somehow get log of x and log of y isolated here, and I'm going to do that by applying these rules. So one of the important habits you should develop in working in this material is notating which rules you're using when you're using it, because it's going to help these things stick with you long term a lot better. Eventually you won't need to do that anymore. When you're first working on homework and practice problems like that, it's good to do that. So what do I mean by that? Well, I have log of x squared times y cubed. So this is a product of two things inside the logarithm. So I'm going to write this as log of x squared plus log of y cubed. So the rule I just used was the product rule, and I'm just going to denote what rule I used. And now I notice I have a power inside of each of these logarithms. And again, I want to have just log of x and just log of y. So I want to get rid of those powers, and so that requires using that power rule. And so that gives me 2 times log of x plus 3 times log of y. And now, log of x we already know is 3, and log of y we already know is 4. So we can replace the entire log of x expression with 3. We're not replacing x here. I want to be really clear. We don't know what x equals. We know what log of x equals. Log of x equals 3. And we know what log of y equals. I want to be really clear. We have no idea what y is. We have no idea, but that doesn't matter because we know what the whole expression is. So this is 2 times, and when we replace log of x with 3, it's 2 times 3 plus 3 times, and we replace log of y with 4. Get that. So this is 6 plus 12, which is 18. Okay, so that's it for our first example. Now, to move on to example 2, you'll see a type of question you will be asked very often. Write log in expanded form. And an analog to this question is write something in condensed form. So a lot of times when we start to do these examples, students will ask, how do I know when to stop? And what does this really mean? So let's just look at this chart, and we're going to just notate something on this chart. So I'm going to move this a little bit out of my way. So whenever I go from the left side of these expressions to the right side, this is what we mean when we say expanding. I should say the double arrows will make that confusing. When I go from left to right, this is expanding because I'm taking a smaller expression and making it larger. And when I go from the right to left side of this table, this is condensing. So the question, if you're asked a question like, hey, expand this expression, how do you know when to stop? It's when you don't have anything that looks like the left-hand side. Right? I can only expand if I can apply one of the rules to an expression on the left-hand side. So if you don't see any of those expressions anymore, you can't expand anymore, and then you're done. And when it comes to condensing, it's the same thing. If you don't see anything that looks like the right-hand side, then there's nothing to condense, and you're done. All right, so with that said, let's go apply it. Write log of the square root of x cubed plus 1 over x squared plus 4 in expanded form. So the first thing I'm going to notice is that I have a quotient here. This whole thing divided by this whole thing. So I'm going to apply my quotient rule and write this as log of the square root of x cubed plus 1 minus log of x squared plus 4. Now, I'd like to see if I could expand this further. I only have 3 options, power, product, or quotient, and I don't see any products in here, right? These terms are separated by a sum, not a product, so I can't apply a product rule. Same thing here, these are a sum. What about the power rule? Oh yeah, the square root is really the 1/2 power. So if I first rewrite this as log of x cubed plus 1 to the 1/2 power, now I can apply the power property, and I get 1/2, right? I just take this power, move it in front, That's what our power property says. If you've got a r times log base a of x, you can move that into and get log base a of x to the r, or vice versa. Take that power from inside the logarithm and move it to a product in front. So that power property gives me 1/2 times log of x cubed plus 1 minus log of x squared plus 4. And again, now the things that are inside our logarithms are separated by sums. They are not factored into products, so there's nothing else to do. There's no quotient, no product, no power. Again, there's powers here, but the important thing is that that power has to be applied to the entire input. R is applied to the entire input of the logarithm. And in these two expressions, our powers are not applied to the whole input. They're just applied to one of the terms inside of it. Okay, so let's move on to another example. Write the natural log of the cubed root of 3x plus 7 times x plus 3 over x cubed times 4x plus 1 in expanded form. So again, I'm going to start with the quotient because I've got all of this thing up top divided by all of this thing in the bottom, right? So I can't do a product really because there's no product of just two things. There's a product of a bunch of different stuff that's also being divided. But I can separate this into one big thing divided by one big thing. And so this becomes, under the quotient rule, the natural log of, and this cubed root, while I'm at it, I'm going to rewrite this as the 1/3 power times x plus 3 minus the natural log of x cubed times 4x plus 1. And now a lot of times students will try to do multiple of these steps at one time, and I understand the desire to try to save time there, but it makes you really prone to mistakes because since we have things like these negatives that pop up with these quotient rules, if you're not doing these things step by step, you're more likely to make a mistake and not apply the negatives in the correct places. So I really suggest just break these down, only apply one rule at a time. Now, when I look at each of these, now each of these expressions inside the logarithm has a product of two things. And so now I can apply the product rule to each of those. So here we get the natural log of 3x plus 7 to the 1/3 power plus the natural log of x plus 3. And now you have to be careful because this negative applies to this whole natural log. So you need a parentheses because you're going to have to distribute that negative. Okay, and now what do we see? Well, we see in this expression, we still have a power, and in this expression, we have a power. And so now we can apply the power property. That gives us 1/3 the natural log of 3x plus 7 plus the natural log of x plus 3 minus, now I'm going to distribute this negative in this step, so minus 3 times the natural log of x minus the natural log of 4x plus 1. And again, now I don't have any pure products or quotients or powers inside my logarithms. Again, like this is a product of 3 times x, but the whole thing needs to be a product of two expressions. So since there's no factors here for the whole thing, we can't apply a product rule. Okay, so now let's move on. And now we're going to write some in condensed form. So write 1/2 log x plus log of y. So hey, order of operations, we got to do what's in parentheses first. So we write 1/2 log. That's the product property, right? You take the two sums and make it a product inside x times y. And now I can apply the power property. Move the 1/2 into the power position. And this is log of xy to the 1/2 power. Now I'm fine with this, but oftentimes you'll see it written as log of the square root of xy. And now we're done. Okay, now when we look at this example, we see we've got a 3 times ln of x and a 1/3 times ln of x squared plus 7. We need to deal with those first, because when we go back up to our rules, what do we notice? Our product and our quotient rule do not have any leading terms. There's nothing multiplied in front of the logarithms, and these rules don't work if you have something in front of the logarithms. So whenever we have a term in front of the logarithm, like r times log base a of x, we have to move that r inside before we can apply our product and quotient rules. So that's the issue that's happening here. So we've got to first take our 3 ln of x minus 1/3 ln of x squared plus 7, apply our power property. That gives us ln of x cubed minus ln of x squared plus 7 to the 1/3. And now we can apply our quotient property. And since we've got the difference between these two logs, we can move this into the quotient inside. And this would be fine, but this 1/3 power, again, you're often going to see this rewritten as the third root, or the cubed root. Okay, that's it for that example. Let's move on. Okay, so now we're going to talk about numbers of digits. So this is a pretty common issue to come up, and it's especially common in scientific topics, because when you're talking about size in the vast scales of space, you're talking about the number of atoms inside a body, it's pretty hard to just list out a number, right? So a lot of times we talk about the size of these things in terms of the number of digits that the numbers have, because that gives us at least some perspective as to just how vastly large they are. So how do we do that? Well, let's consider the question, how big is a number? So what do we mean by how big is a number? Well, we will consider the size of the number to be how many digits are left from the decimal point. So for this purpose, we say that 4,712.647 has 4 digits, because we're just looking at the part left of the decimal place. So how do we do this? Well, let's think about what we do know. So if we take some number k that has n plus 1 digits, that means it's a number between 10 to the nth power and 10 to the n plus 1th power. So if you don't see exactly what that means, well, think about this. If I have, say, 352, that's between 1,000, which is 10 cubed, and 100, which is 10 squared. Right? That's what we're saying. So if you have a number, k, with n plus 1 digits, then k is between 10 to the n plus 1 and 10 to the n. The key part here is that the number of digits is this exponent. That's what we're keeping track of here. This exponent on this upper bound, 10 to the n plus 1, that happens to be the same as the number of digits for k. So then if I take log base 10 of this inequality, I get log base 10 of 10 to the n is less than or equal to log base 10 of k, which is less than log base 10 of 10 to the n plus 1. And what do we know? Log base 10 of 10 to the n is n, and log base 10 of 10 to the n plus 1 is n plus 1. So all this says is, if the number k, if you take log of k, the next biggest integer is the number of digits. So in other words, a positive number k has n plus 1 digits if and only if log of k is greater than or equal to n and less than n plus 1. Now this is very important because the number of digits is always the upper bound. If I got, for example, that log of k was 3,532.1, then k has 3,533 digits. The key here is that this is not rounding, and that's the really common mistake students make. Students often think, oh, this means round. Just round. Take log of k and round. That's not what it means. N plus 1 is always the next integer up. It's the next biggest integer. So if I take log of k and I got something like 3,532.1, it's the next integer up. That's 3,533. Right? It doesn't matter what you get here. It's the next one. Okay, so with that being said, let's go ahead and find the number of digits in this. So one of the issues here, and the reason why these logarithmic properties are so important, is because a lot of times our calculators can't compute these numbers directly because they're too large. If you try to type this into your calculator for this class, maybe if you use a computer algebra system, it'll be fine, but the regular calculator for this class cannot handle a number this big. It's going to just spit out an error. But it can compute the log of this thing because we can use log properties to simplify the computation. So I'm looking here at log of k. This is my k. So this is log of k. And what I'm going to do is first use my product property to split this up into log of 17 to the 200 plus log of 53 to the 67. And then I'm going to use my power property to write this as 200 times log of 17 plus 67 times log of 53. So why does this make such a difference? Because your calculator, if you're writing it in this form, has to first compute this huge number and then take the logarithm. This number is gigantic. It can't handle this number. But using our product properties and our power properties, we can turn this into numbers that are much smaller and easier to compute. Even though they have the same value, it's the order of operations issue that first your calculator would have had to do this, and it can't do this on its own. So we use our properties to rewrite this, get 200 log of 17 plus 67 log of 53. So let's go ahead and evaluate that. I'm just plugging it into my calculator here. Okay, and so I get that this is approximately 361.61. And that implies that the number 17 to the 200 times 53 to the 67 power has 362 digits. I always go up one, right? Whatever number I had here, the next number up. The next whole number. Okay, so that's it for that one. All right, which number is bigger? 5,432 to the 9,876 power, or 9,876 to the 5,432 power? Well, if we know the number of digits that each of these has, then we'll know which one is bigger, right? So here we can just start by saying, taking log of 5,432 to the 9,876. I'll apply my power property. That's 9,876 times log of 5,432. And now this is something my calculator can handle. And my calculator says this is approximately 36,886.46. So what does that tell me? That tells me that 5,432 to the 9,876 has 36,887 digits. Again, notice I'm not rounding, I'm going to the next integer up. Right? If you rounded, you'd get 36,886. That would be wrong. That's not the number of digits. It's always the next integer up. Now, on the other hand, when we look at log of 9,876 to the 5,432 power, that's 5,432 times log of 9,876. And we'll plug that into the calculator. That gives me approximately 21,698.56. So that implies that 9,876 to the 5,432 has 21,699 digits. And now all we got to do is look at which one has more digits. Oh, this one has more digits. So 5,432 to the 9,876 is bigger. Okay, so wow, I wrote myself right out of room there, didn't I? Well, I apologize if you're writing this and you ran out of space there because you were writing as big as me. I really did not need to write that big. So I'm just going to shrink this work down a little bit and give myself some space to do the other problem here. I'm actually going to do number C on this side here. Or part C, I should say, not number C. Estimate pi to the 650 power using scientific notation. Okay, so we've got y equals pi to the 650 power. And the way you should think about this, what is scientific notation? Well, scientific notation is like x dot y z times 10 to a power. So in other words, when I say I want to write something in scientific notation, I want to write it as a product of a decimal with one digit here to the left of the decimal place and 10 to a power. So you can kind of think of it in this context like I have a base pi here, but I don't want a base pi, I want base 10. So you're kind of like trying to figure out how to switch from base pi to base 10. So that's how we can think about this initially to get started. And that gives us a hint that, hey, what if we took log base 10 of both sides? And then we'll see why that works momentarily. So if I take log base 10 of pi to the 650, well, it lets me do something very nice. So now I've got log base 10 of y equals, and I can use my power rule to move the 650 in front of the logarithm. This becomes 650 times log of pi. So now I don't have that exponent with the pi anymore. Now we're in logarithmic form, so I need to be an exponential form base 10, but I can now plug this thing into my calculator, 650 times log of pi, and that gives me that log base 10 of y is approximately 323.15. But I don't want log base 10 of y, I want y. Y is the number that I'm trying to express with this power of 10. What can I do? Oh, well, I know what undoes the logarithm, the inverse function, base 10. So if I write 10 to the log base 10 of y this is approximately 10 to the 323.15. So in other words, y is approximately 10 to the 323.15. Now, that gets us really close to where we want to be. But notice the whole thing about scientific notation is that this power is an integer, not a decimal. So I somehow have to split this up a little bit further. So one of the ways I can do that is by thinking of this number, 10 to the 323.15, as 10 to the 0.15 plus 323. And then I can use my exponent property. Since I've got a sum inside the exponent, I can split this up to 10 to the 0.15 times 10 to the 323. Now I have an integer here. Let me clean this up a little bit. And so now finally 10 to the 0.15. What is 10 to the 0.15? It's about 1.413. And there, that's my answer in scientific notation. 1.413 times 10 to the 323rd power. So again, just to recap that process, we started with y equals pi to the 650. So we took base 10 logarithms of both sides. Because the logarithmic rules let us rewrite this as a product of 650 times log of 10, which I can then evaluate in my calculator. And then just to get back to y, instead of having log base 10 of y, we apply the base 10 to each side. And that gives us y equals 10 to the 323.15. All we've done here is rewrite 323.15 as 0.15 plus 323, and then we just applied our exponent property to split this thing up, and then we're good to go. Plug that into the calculator, and that's your scientific notation. Okay, so with that one done, let's go on to the change of base formula. So the change of base formula is a really useful tool, and it comes up a whole lot in mathematics and applications. Now, where students end up using it most is to evaluate things in a calculator. Because, well, long story short, there are infinitely many logarithms, and the way that calculators compute logarithms is by storing some data that comes from analysis of functions that's like really Calc 2 material. And it uses that data to evaluate the logarithms. But since there are infinitely many logarithmic functions, it can't store infinitely many bits of information, infinitely many chunks of data. So instead, it only stores, most calculators only store the data for the natural log and the log base 10. So most of the time, you'll use the change of base formula to simply convert to one of those two logarithms, and then you'll just plug it into a calculator. But there are other interesting things we can do with the change of base formula as well. So the first of all is, what is the change of base formula? Well, let a, b, and x be positive real numbers with a not equal to 1 and b not equal to 1. Then log base b of x can be converted to another base as follows. Log base b of x equals log base a of x over log base a of b. The key thing here is a can be whatever you want. It doesn't matter what you pick for your new base a, it will always work. It will always be equal to log base a of x over log base a of b, as long as a is a positive number not equal to 1, because that's all logarithmic bases can be. So typically, the most common ones you will use are the natural log of x divided by the natural log of b, or log base 10 of x divided by log base 10 of b. That's the most common ones. Okay, so this is a weird thing, right? It should seem a little odd How in the world is this true? So let's take a look at the proof. And the proof is actually very simple, yet somehow it seems tricky when you read it, even though there's nothing crazy. So just one step by one step. First, we're going to just write log base b of x equals y. We're just essentially giving this logarithm a name. We're calling it y. So I know that I can switch my inputs and outputs, and that's going to give me b to the y equals x. So now if I take log base a of both sides, and notice it doesn't matter what base a is here. I haven't specified, hey, I picked such and such for a. There's nothing like that. I'm just taking log base a for both sides. And then, what does that give me? Log base a of b to the y, I can apply my power rule and move the y in front of the logarithm. So now I have y times log base a of b equals log base a of x. I divide the log base a of b across, and I get y equals log base a of x over log base a of b. But y was log base b of x, right? They're the same thing. So, in other words, this is just another way to write your logarithms. So, let's go ahead and use this to evaluate this log base 4 of 8. Now, you could use the natural log or base 10 and plug it into a calculator. But what I want to show is that clever choices of bases can sometimes allow you to avoid that entirely. So what I notice here is that let me rephrase that. What I notice here is that 8 and 4 are both powers of 2. So what I'm going to do is apply my change of base and choose base 2. So that gives me log base 2 of 8 over log base 2 of 4. And the reason I did that was because since 8 and 4 are both powers of 2, I can take this log base 2 of 2 cubed and write this as log base 2 of 2 squared. And now we can just apply our basic definitions for inverse functions. Log base 2 of 2 to the third is 3. And log base 2 of 2 squared is 2. So this is 3/2. No calculator required. Okay, now on the other hand, if we look at this example, log base 7 of 13, well, log base 7 of 13 and 7 are not powers of the same number, so we're not going to be able to do any clever tricks like the last one, but we can just use change of base and write this as the natural log of 13 divided by the natural log of 7, and then we can go to our calculator and say, hey calculator, do that for me. Log of 13 divided by the natural log of 7, which is approximately 1.32. Okay, so now we're going to move on to half-life formulas. So this ties into things that we talked about before, like exponential growth and decay, in particular, exponential decay. So in the case here, the way I'm writing exponential decay is a0 times e to the kt, where k is negative. So before I wrote it where k is positive, and then I put a negative k in the formula. There's really no difference. It will change how your expression looks slightly, but it doesn't make an actual difference in terms of the arguments or the way the formulas work, right? So if we write our formula in a way that k is a negative number, so we have a0 times e to the kt, then the half-life, which is the time it takes for a substance to reach half its starting amount, is given by h equals negative ln of 2 over k. So in other words, like if we talk about radiation, how long does it take the radiation to decay to half its levels? That's the half-life of the radiation. So that means that we're trying to solve for the time t such that a of t equals 1/2 a0. So just plug that into our equation, right? A of t equals 1/2 a0 gives me 1/2 a0 equals a0 times e to the kt. Divide by a0, I get 1/2 equals e to the kt. Take the natural log of both sides, I get the natural log of 1/2 equals ln of e to the kt. But of course, the natural log of e to the kt is just kt. And here I rewrote the natural log of 1/2 as ln of 2 to the negative first power. Then I put my negative 1 power in front. That's negative ln of 2 equals kt. And finally, t equals negative ln of 2 over k. So this is specifically the time that the substance has decayed by half. So we typically will label this in a formula as h equals negative ln of 2 over k. Okay, so let's take a look at this example. Determine the half-life of a substance that decays from A0 equal to 250 to A equal to 70 and T equal to 15 years. So in order to do that, we have to find K. So generally with these kinds of problems, the first thing you have to do is figure out what are you missing. So if I want the half-life and half-life is negative ln of 2 over K, that means I need to know what K is. So I've got this information given. So let's go ahead and plug it into our formula and see what happens. So A equals 70. So we've got A of T equals A0 times E to the KT. So 70 equals 250 times E to the K times 15. And I want to solve for K. That's the first thing I need to do. So if I divide by 250, the 10s will cancel and I'll get 7 over 25 equals E to the 15 times K. I just changed the order of the multiplication there. And now if I take the natural log of both sides, I get ln of 7 over 25 equals the natural log of E to the 15K. But the natural log of E to the 15K is just 15K. So this tells me that ln of 7 over 25 equals 15 times K. And so to solve for K, I just divide by 15. So K equals the natural log of 7 over 25 over 15. Now, I don't just want K. Remember, what we were asked for was the half-life, but we needed K to solve that. So our half-life, we just plug K now into our formula for half-life. Negative ln of 2 divided by K, which is ln of 7 over 25 over 15. Now this is division by a fraction, so I'm going to rewrite this as multiplication by the reciprocal. And at this point, this is just plugging stuff into a calculator. So what do we get? We get negative 15 times the natural log of 2 divided by the natural log of 7 divided by 25. That's approximately 8.17. So roughly the half-life of this substance is 8.17 years. Okay, and let's go ahead and take a look at one more thing. So here we're given a half-life of a medication. The half-life of the medication is 15 hours. Estimate the time for the drug to decay to 80% of the original amount ingested. So I need, in this case, to solve for time, where amount at time t equals 0.8 times the initial amount. So I need to solve for 0.8 times the initial amount equals A0 times e to the kt. And if I divide by A0, I get 0.8 equals e to the kt. And if I take the natural log of both sides, the natural log of 0.8 equals k times t, right? Natural log of e to the kt is just kt. I need to solve for t, but that means that I need k. Well, how am I going to get k? Oh, well, they told me the half-life was 15 hours. So h equals negative ln of 2 over k. So 15 equals negative ln of 2 over k. So if I multiply the k across and divide by 15, I get k equals negative ln of 2 divided by 15. And now I can plug that answer into here, and I get t equals ln of 0.8 divided by negative ln of 2 over 15. And again, division by a fraction is multiplication by the reciprocal, so I can write this as negative 15 ln of 0.8 divided by ln of 2. And then I can plug all that into a calculator and say negative 15 times ln of 0.8 divided by ln of 2. And I get approximately 4.83 hours. Okay, well, that's it for this one. Thank you for watching.